Hello friends. The topic of my discussion today is the field equations of the Maxwell and in terms of the scalar and vector potential. Hope you must have read in your undergrad or MSc about the scalar and vector potentials. And I will tell you in detail about the concept of that potentials. And there is a new concept. There is a called retarded potential. So one by one, I will describe you in a very easy way. You will not get bored. So you must have read in this many. I have seen this in many places, but one by one, I will be talking about this so that you will have no problem. So, and if you have any problem, please let me know. Please subscribe my channel so that you will get notification of it. And this is one of the lectures of my electromagnetic theory. So previously I have talked about the electromagnetic field equation, wave equation, electromagnetic wave in the conducting and the non-conducting medium. So before going through this lecture, I request you, all of you, please just read my previous lectures so that you will get a thorough knowledge of what are Maxwell's equation, what are Gauss law, what are first to fourth equation. Okay, so let's start, friends. So first is the introduction to scalar and vector potential. This is the four laws of Maxwell. First one is the Gauss law. Second one is the Gauss law for magnetism, Maxwell's second equation. Third equation is the Faraday's law and the electromagnetic induction. And fourth one is the another curl of this Ampere, the modified Ampere's Maxwell's law. So all the details of all of this Maxwell's equation have been previously described by me in my all of my lectures. So please go through that. I request you. So first equation is divergence of B is equal to 0. So non-existence of magnetic monopole. And from this, what we can get, B can be expressed as the curl of A. From the vector equation, vector algebra, you can get the divergence of curl of any vector is the 0. So what is A? A is the electromagnetic vector potential. Is a quantity what we just nomenclature it as a electromagnetic vector potential. So simply from the divergence equation we get the A term. So what is A? So but actually in a real problem we need to calculate the magnetic vector potential. So from if we know the equation, the form of A, so we can from that we can get to the B. What is B? So there is another equation of Faraday's law, curl of E, we can write it del B del T. So we substitute the value of B in that, what we can get, curl of E is equal to the minus del T of curl of A. So we keep this term in the left hand side, curl of E plus del A del T is equal to 0. So curl of any quantity is 0. What we can represent it, if the curl of any quantity is 0, we can write as a negative of the potential. Okay, if this term is 0, so this is also from the vector equation, vector algebra. So how can we describe phi? Phi is the electromagnetic scalar potential. So in terms of phi, how we can write the electric field minus grad phi minus del A del T, as curl of grad phi is 0 from vector potential. So if we know, so you please just remember this quote. If we know the equation, that the solution of phi and A, in turn this solution will lead us to the derivation of electric field, and if we know the value of vector potential, that will lead us to the value of B. And in our real problem we need to calculate the electromagnetic electric and the magnetic field, now the electromagnetic scalar and the vector potential. If you know the value, so our objective is to calculate the form of A and B, means A and phi, electromagnetic scalar and the electromagnetic vector potential. Now how we can get to the field equation? Little bit derivations are there, but I think I have made it in an easy way. You know, in a linear dielectric medium, the electric displacement vector can be written as proportional to electric field, and the magnetic field proportional to magnetic intensity, magnetic field intensity with the linear term mu and the epsilon previously I have told. So starting from the equation curl of this H, Maxwell's fourth equation, what we can get? We get this term. Now in turn we substitute the value of magnetic field, curl of A, and we substitute the value of also electric field. So from vector algebra we get this term, this term just turns out to be in the two terms, grad of divergence of A minus grad square A. And in the right hand side what we can get? In the right hand side we got three terms, okay, because there is mu phi last term, del T of grad phi, okay. So what we can get? Grad square A minus mu epsilon del square A del T square, and there is a term, this term, I will tell you the significance of this term, we put it in a bracket, is equal to right hand side there is a source term. And now you can write this grad square minus 1 by c square. This is the 1 by root over mu epsilon is 1 by c square, velocity of light. I have discussed it in one of my previous lectures, the velocity of light in vacuum. So we can this will be a D'Alembert operator. So this operator will be grad square, del square minus 1 by c square del 2 del t square. Okay, this is the first equation of the Maxwell's field equation in terms of the vector potential. Now if the same equation we can derive it for field, in terms of A we can get it phi, means Maxwell's scalar potential, that means scalar potential. So how can we get? We took the equation from that Gauss law and substitute the value of electric field. In the same way we will do the derivation. Please follow this. I will request every one of you to derive it by their own, so that they will get a clear understanding. Yes, so in for the easiness of the calculation we put these terms, divergence of A plus mu epsilon del phi del T, and this is in the brackets in the same way. So we come to the last term, and this is the Maxwell's field equation in terms of the scalar potential. So it's a Maxwell field equation, the vector potential, and a Maxwell's field equation in terms of the scalar potential. Okay. So in a static case, how it will get? So let's move to the next. This is our Lorentz-Gauge condition. What is that? In the previous slide, there is a term in the parenthesis, divergence of a mu epsilon del phi del T is equal to 0. This is called the Lorentz condition. So Lorentz maybe is a Lorentz gauge. It's better to call it as a Lorentz gauge condition. So these are the field equation. I again write it for your convenience. There is a right hand side, there's a source term. This is J, current density. This is rho, charge density. So if with the value of 0 this term, what you can get? Grad square A and these two terms for the Maxwell's field equation. This is the actually wave equation with inhomogeneous. If there is a 0 in the right hand side, how you can get? You will get it, you will reach to the wave equation. But this is the wave equation with the source term in the right hand side. So better we'll call it as the inhomogeneous source term. So you can see that one by one we are just deriving these things in a very easy way. So many of the students are afraid of deriving this, but not. I will tell you, if we start it from the very basics, you don't need to remember anything. I don't remember it. Yes, so you just calculate it by your own. You know the Maxwell. Yes, you need to remember the Maxwell field equation. You know Maxwell's field equation. So Maxwell's equation, 4 equation. So from that you know vector algebra. From that you derive E is equal to minus grad phi minus del A del T. B is equal to curl of A. You substitute this in the Maxwell's another equation, and you conclude to the term, and you put the Lorentz-Gauge condition. You remember that divergence of A plus mu epsilon means 1 by c square del phi del T. This term is called Lorentz-Gauge condition. So this term is 0. So you will conclude reach to the term of Maxwell's wave equation. This is a wave equation in a inhomogeneous term in the right hand side. So this is called actually box operator in previous slide, grad square minus 1 by c square del phi del T square. This is the box operator. So better we'll write grad box square A is equal to minus mu J, box square phi is equal to minus rho by epsilon. Now, if the potentials are time independent, it did not depend on time. That is simply in the statics case. So what we can get? This term will be 0, this term will be 0. There will be no t dependence of A and phi. So we'll conclude to grad del square A is equal to minus mu 0 j, and grad square phi is equal del square phi is equal to minus rho by epsilon 0. So can you remember it? Yes, it is the Poisson's equation. If there is a 0, then it is a Laplace equation, and there is a source term in the right hand side. This is a Poisson's equation. So you know the solutions of the Poisson's equation. For scalar potential, what you'll get? You'll get this integration of rho dv. There is a many charges are integrated to the volume element. This is a q by total charge by r. And therefore vector potential, you replace rho with the current density with the source terms divided by, this is actually, I will detail to tell you about this term r minus r prime. It's a distance from source to the field point. Okay, so pictorially if you can see it, you will get a better understanding, not by seeing. And for time dependent, that means non-static case, for non-static case, what we can get? You can get the box square phi operator. This you can get, this is a box square A means minus mu 0 j. We took it as a vacuum mod A. You can also put it mu j. So I take it as a vacuum, or mu is mu 0, phi is phi 0, free space. And box square means del square minus 1 by c square. You remember this term box square operator. So for non-static case, the Maxwell's field equation in terms of the scalar and vector potential will be like this. So this is the final equation, and here then you can get the concept of retarded potential. This is called the D'Alembert wave operator, and this is actually inhomogeneous phi and A equation for the scalar and vector potential. So if you know the form of scalar potential phi A and AR, R means that the field point, the point at which we are evaluating the potentials, we can in turn get to the value of electric and the magnetic field. That means electric field is E and the magnetic field is B if we know the value of scalar and the vector potential. Okay, so hope I am able to make you understand up to this part how we'll get to the Maxwell's field equation in terms of the non-static case. So now we'll see the solution of phi and A for the non-static. And here comes the concept of retarded potential. So if the field is at RT and the source point is at R prime T prime, so how we'll relate it? They are related like this equation. What is that? T prime is the retarded time. Means retarded means is the early time. This means time taken by the electromagnetic wave to travel from source point to the field point. Let's see, this is a source point R and T, and there is the field point R prime T prime. So what will be the distance between that if you calculate from the origin? R minus R dash. So that is we represent it as capital R. So this R minus R dash. So how the electromagnetic wave will time taken? So this time is called retarded time, at which point the field point, though how the electromagnetic wave when the emanating from the source point. So we know accelerating charges produce electromagnetic waves, and there is also scalar and vector potential as a produced. So retarded potential, they are generated by the electromagnetic waves of time varying charge or current distribution. Means J is dependent on time, and also rho is also dependent on time. Actually they have left the point in a past, and as electromagnetic field propagate with the speed of light, the potentials also travel with the speed. So we'll get that retarded potential. So what we can get? So you see, this is the actual pictorial point for convenience. This is the source, this is the origin, this is the source point. We assume a small volume element dv prime from O to F, means this distance is R. It's a field point at which potential is to be evaluated. This is a source point, that means R dash T dash. So you will better denote it R dash T dash, and F field is R and T. So let's take this, let's see this picture exclusively, and the distance that matters, that is source to the field point, where you need to evaluate the potential. At any point that electromagnetic field has left this point at a time t prime, and we need to calculate that time t prime, which is an earlier time. So this is the time t, and we subtract it from the distance, that means this distance by c. So if we do that, you get the value of retarded potential, the potential at an earlier time, which are generated by the time varying, that means in a non-static case simply. So what is the Minsky, what is the general solution of it? In previous slide I have shown you there will be no time dependence, only phi r. So we put it as a time because this point we are evaluating the potential. Now at a source point we put the value of t prime, that means the time at which the electromagnetic wave left that source point, and that point is utilized in evaluating the potential at the field point. Not that time matters, that time matters is t prime, which is there in the source term, t prime and t prime in the rho and the j. These are called retarded potential, that means potential at earlier time. This is the time delay between electromagnetic wave emission and the moment at which it reaches the observer, means there is an observer. Suppose at 12 o'clock the electromagnetic wave left this point and we are recording this point at time 12:15. So at what point we will get the retarded field that t is 12:15. So there is an earlier time 12 o'clock. What we can get it from this equation, t prime is equal to t minus this. Okay, I hope you have understood. So let's, for your convenience, I have put it. Distance means velocity into time. So what this distance travels means this distance, r minus r prime, and the velocity with the c velocity travels, and time means this t prime is the time at which left the point and t is the time. So t minus t prime. So from there we can easily get the t prime, and we will represent this t prime which is utilized in evaluating the potential at a point of field. So these are called retarded potential, which are produced by the time varying current or charge distribution in the past. Yes, you just remember it. Yes, this I have told you already. The field actually start propagating at an earlier time, and t is the later time at which we evaluate the potential for the observer. So this is the whole concept of the retarded potentials, and this is this form for the retarded potential, means non-static case. What will be the form of phi? So the same equation is there, same picture is there. This is a source and field point observer. So non-static case, the value of source term actually doesn't matter, and with the status of phi and a are determined by the status of rho and j at earlier time, because in my equation I have put the rho as a function of t prime and j as a function of t prime, and the electromagnetic information takes a finite amount of time. This amount of time to take a travel with a time delay, that means r minus r prime by c. That means this is the time distance by a, this is the time delay. So you know the value of potential at phi rt. So obviously this solution will satisfy this equation. So I request you all to do it in hand to put this value. This will little cumbersome equation. I will show you in one of my in any of my next lectures how will the solution of phi and r and t and art will satisfy the inhomogeneous equation. So we put the value of phi and a with grades, will replace all the values of this and see whether they are satisfying this equation. Okay, I have denoted as a t prime. You can also denote the retarded potential state. There is nothing in it because r is a retarded. You will have a convenience in that. Okay, so I hope you have understood. This is the concept of retarded potential. Now show you the practical example of retarded potential, how you can feel it, the retarded potential case. Yeah, so there is a sun is there, and you know this is a 1 astronomical unit away from our earth. Okay, and the sunlight takes an amount of 8.33 minutes to reach to the to reach to the earth, our mother. So what we record the time, it's 8.33 minute delay, and it actually the light left from the sunlight at 8.33 minute ago. So this is a retarded time. This time ago it has already passed, I mean just left from the sun, and we are recording. So I think there are no instrument in that. How we can, if the sun is not there, the sun actually switched off, if we assume, then we don't have any recording instrument by which we can measure at what time ago the sun has actually disappeared. Okay, so there is also practical case of many stars. Many stars, you see the lights of it. Okay, but you don't know, they are far away, many astronomical units away from us. So you don't know actually ki, from when the light has emitted from the stars. Maybe the stars at the present time we are seeing actually not now, they might have extinguished. There are not any case of that I mean suns, that stars, the existence of the star, they might have extinguished it, and now we are just seeing that leftover part. Okay, so this is the real case, so you can feel it. Okay, hope I have um, but the sun is not too much away from us compared to many stars, so we get the light 8.33 minute after from which it left the. So friends, now I hope you have understood my lectures of that scalar vector, electromagnetic scalar vector potential with an appropriate example of it, so that you will not forget. So this is my channel, some in with physics and geophysics learning with the electromagnetic theory principle, and hope you have liked it. And if you want to get more updates, please share, like and follow, comment, and turn on the bell notification icon for getting more updates. Thank you.